Hello, this is Mr. Ware, and thank you for checking out Mr. Ware's videos. This is part 2 to a video I am doing to go over linear and exponential functions. Alright, so here um, we're talking about, again, trying to determine between linear and exponential functions in context. So in context, we've got, like, basically means word problems. So basically it's going to give you um, um, a lot of different things here, and you got to pick whether it's linear or exponential or whatever they say to do. So sometimes it's a little tricky, but let's look at this first one here. So which of the context below could not be modeled by an exponential function? So it cannot be modeled by exponential function. So they look for things that are not exponential, which means they look for things that are not multiplied or divided even. Okay, so that's what we'll take a look here. So let's look at A. Okay, the amount of a certain medicine in a person's bloodstream decreases by 1/5 every day. Okay, oh, forgot to put that in there. But again, not exponential. Okay, so probably looking for something to maybe add or subtract. But like I said, 1/5 every day. So it decreases by 1/5, which means you have to multiply by 1/5 or divide by 5, which means that doesn't work. Okay, let's look at the next one. A radioactive compound decays at a rate of 30% per hour. 30%, that's where I have to convert it to a decimal. It decays, so you're going to add it with subtract it from 1 and then multiply that number. So since we're multiplying, it's not that means it's exponential, so not that one either. Okay, a coin collection appreciates at a rate of 6% per year. Convert to a decimal, add to 1 this time, but still multiply. This is exponential, so not that one. An amusement park charges $3.50 to go on each of the rides. $3.50, $3.50, $3.50, $3.50 every time you go on a ride. So you're adding $3.50. So this would be correct. Okay, that's the one that's not exponential. Okay, let's take a look at another one. Okay, which of the contexts below represent exponential decline or decay? So it could be exponential, but it has to be declined or decay. It has to go down. All right, so elevator descends at a rate at 12 feet per second. 12 feet per second. 1 second, 12. Another second, 12. Another second, 12. You're adding, or in this case, subtracting 12 each time. That's not exponential. So A wouldn't work. You're subtracting 12 or adding a negative 12 each time. So that doesn't work. A car depreciates at a rate of 8.4% per year. You would convert it to a decimal, right? And then subtract it from 1. It's going to depreciate. So this one would be yes, because it depreciates at 8.4%. That lets us know it's exponential and it's going down. Now let's take a look at these other options. C doesn't work because it triples, which means it's exponential, but it's increasing. Okay, and D is also exponential, but it's appreciating. It goes up. All right, let's take a look at another one. Okay, which of the context below could be modeled by a linear function? So basically we're looking for something where you either add or subtract. Forgot to put the the thing like I did before. But here we've got a smartphone data plan charges $45 a month at 1.17 gigabytes of data use. So every month they're going to charge you 45, 45, 45. Okay, that's linear because you're adding 45 every month. And even when you look at the data used, it's 1.17 every data gigabyte. So you're adding that. Let's take a look at the other ones. B, coin collection appreciates. That's exponential because you got a percentage here. Okay. C, the amount of certain medication in a person's bloodstream decreases by 1/2, dividing by 2. So that's going to be the same as multiplying by 1/2, which means it's exponential. All right, a car depreciates at a rate of 2.7% per year. All right, that's going to be exponential, so it's not linear. So that's a quick little look at some of those problems. All right, let's take a look at some more different types of problems. All right, here, what we want to do is determine the domain of the following graph. Okay, so what I'm going to use is interval notation. Okay, so domain is going to be everything on the X. So we're just going to look on this X. Now the graph goes up, down, up, but we're looking at the X. How far left does it go? How far right does it go? Because it's asking about domain. Okay, so I put little lines here to show you how far left it goes and how far right it goes. All right, see that line? Okay, so then I circled the numbers on the X axis, 9, -9, and 11. So it goes from -9 all the way to +11. And because we got these filled in dots, we're going to use brackets instead of parentheses. So that's going to be a bracket, -9, comma, 11, and another bracket. Now if it's an open circle, you put parentheses. If it comes to, let's say, the top of this, if we're doing range, you're going to use the parentheses too. But if you come to a closed circle, put bracket because it includes that number. All right, let's look at another one. Okay, let's determine the range of the following graph. So now we're talking about range. So with range, we're going to look at the Y. So all the numbers are going to be on this axis. So we want to know how low it goes to how high it goes. All right, so here I drew little lines again, dotted lines right here. Right? So it goes to here to here. Now remember, don't look at X. We're not looking at this one. We're looking on the Y axis right here. Okay? So that's going to be from -2 to 8, going low to high here. Now on the low end, we've got this parentheses because of this open circle. And on the top end here, we've got a bracket because of the closed circle. I probably got my bracket the wrong way. We'll turn it around in a second here. But we're going from -2 to 8. So we're going to put a parentheses around the -2, comma, 8, and put a bracket around that. All right, let's look at the last example here. Okay, determine the domain of the following graph. So now we're doing domain again. So that means we're looking at the X. The X. So how far to the left does it go? All the way to -10, closed circle. All the way to +10, closed circle again. So because of those closed circles, -10, +10, we're going to have brackets. Bracket here and a bracket there. So from -10 to +10 in brackets. All right. So now one more thing I want to show you that deals with discrete and continuous and linear and exponential. So just one moment. Okay, so this is sequences versus functions from a graph. So we're taking a look here, and we want to use the graph to fill in the answers to the sentence below. So here's a graph. It is this type of line. It's going this direction, stopping right here. Okay, so it says the graph is and then it gives you a little drop down where you pick a choice here. So continuous line or curve, or a set of discrete points. Well, it's obviously a line, right? So we're just gonna put line. Its domain can be best be described as a set of the, all right, now real numbers or whole numbers. Well, if it's going to be dots, it's going to be whole numbers. But this one is continuous, so we're going to use real numbers. For every unit the x increases, the y grows or declines by repeating what? This next one here is asking, are we adding? Are we multiplying? So it's a straight line, so we're adding. Okay, and as a result, the graph could be said to represent a linear function. So if it's a solid line, straight line, not curve, it's going to be a linear function. Okay, and it gives you this little graphic organizer: discrete or continuous, additive or additive, or multiple. I can't say those words, but are you adding or multiplying here? And so since it's continuous and you're adding, it's a linear function. All right, let me look at another example. All right, use the graph to fill in the answers to the sentence below. So here, this graph above is a discrete set of discrete points. See the points? A set of discrete points. Its domain can best be described as a set of the whole numbers this time. Whole numbers. Not all real numbers, just the whole numbers. Alright, for every unit the x increases, the y grows or declines by this repeated process. You're going to be multiplying. Either you're dividing or multiplying here. So it's multiplication. And as a result, the graph could best be said to represent a geometric sequence. And that's it. That is a Delta Math review for Unit 2. I want to thank you for checking out Mr. Ware's videos. Have a nice day.